case we would have some dead code and we might find false positive information flows. And when looking at this, trying to discharge these false positives, it's very hard because the auditor has to basically understand someone else's code. So information flows aren't local properties. They're a global property of the application. And similarly, even looking at a piece of code and trying to determine whether or not it's reachable is in some sense a global property of the application. You have to understand the semantics of an application as a whole instead of just some small few lines of code. And it's very hard, it's already hard to understand someone else's code. But furthermore, when you're an auditor looking at an app, you usually don't have source code. So you're looking at the, in this case, the Dalvik bytecode, trying to figure out what it's doing. And furthermore, oftentimes developers will obfuscate their code. So the method names are just meaningless, like character sequences that don't make any sense. And this makes it very difficult for the auditor. And the question we wanted to ask is whether we can shift some of the work to the developer. So ideally, what we would want to do is take our app, run it through the static analysis, get some information flows, and possibly imprecise. And we're going to look for some piece of dead code that might be a source of false positives. So we're going to take this piece of dead code, ask the developer, okay, is this piece of code actually dead? And then the developer can answer either yes or no, and then we can refine the results of our static analysis. And this way we can get rid of all of the false positives we find that are due to dead code. So this would be great if the developer answers truthfully, but obviously the developer might be adversarial. So if I'm making a piece of malware, I would just say that all of the code is dead, so all of the flows you found are false positives. And our solution is going to be to somehow enforce the response that the developer gives. So there are two cases we have to consider. In the first case, let's say the developer answers yes. Okay, so this piece of code is dead. Then we can update our results. But in order to make sure that enforce the developer's response, what we're going to do is we're just going to delete the code from the application. So the developer said it's dead, so it really shouldn't matter if we delete that code. So we'll just delete the code from the app and publish the partial app on the App Store. Alternatively, if the developer says, no, this code is not reachable, this doesn't directly cause any malicious effects, but it might. We don't want to be in the situation where a developer just says, yes, everything is reachable, so that they don't have to do any work and we won't remove any of their code. So we're going to require that the developer submit a proof that the code they claim is reachable is actually reachable, and we'll just have them give a test case that executes the reachable code. And finally, we have to account for the possibility that we can't find any such queries. This will happen if the information flow is not, or the false positive is not due to dead code. And in that case, we're just going to have to fall back on the auditor to filter out the remaining false positives. But as I'll show later, a lot of our false positives are actually due to dead code, and this can be a very effective method for removing those false positives. And then everything else falls to the auditor. So our queries to the developer are going to be what we call cuts. So a cut is formally a piece of code that is potentially dead. And also removing the cut from the app breaks all the potential information flows that our static analysis finds. And a valid cut is just going to be a cut that the developer confirms to be dead. So I'll just give a quick kind of intuitive overview. So here I have a diagrammatic representation of a source sink flow. So the red box is the source, the blue box is the sink. And there's a flow from the source to the sink in this graph. So what we're going to do is we're going to first say everything is dead. And a cut is just going to be a subset of these edges. So for example, this edge by itself is not a cut. These two edges are a cut because if we remove them, we break the source sink flow. And we'll also look for a min cut just to minimize the work that the developer needs to do. So the developer says this is not a valid cut, and we update our knowledge about what code might be, what code is reachable, and then we find another min cut. Maybe the developer says this is a valid cut, so we'll just remove it from the program. So the query is going to be a list of statements that correspond to the edges that we cut. And the developer response, as I said earlier, is just a test case that executes the reachable statement. And in addition to being verifiable, we think there are a number of benefits to using test cases. First of all, developers routinely write tests, so they can just give us the tests they've already written. Second of all, we can seed the results with dynamic analysis. And finally, I think this is pretty important, we can actually use the test cases to aid the auditor downstream. So they have some tests that actually execute all the parts of the code that might be related to the information flow. So just to recap, our process for interactive verification, first we do the sound static analysis, and then we find a cut and query the developer to see if the cut is valid or not. And then either we update the potential dead code and repeat, or if we found a valid cut, then we delete the valid cut from the program, publish the app on the App Store, and we're done. And this interactive process is just going to come with the light, static, and dynamic analysis that there was previously. So now in particular, there are no false negatives flowing onto the App Store, and we've still hopefully maintained a small level of false positives to pass on to the auditor for manual inspection. So now I'll go into a little bit more detail about how we actually find valid cuts. So just as an example, we have the following app on the left-hand side. So this app, at a high level, it has two runnables, and it's going to call one of them. But if our app can't figure out which one it's calling, if our analysis can't figure out which runnable is being targeted, it'll assume that both of them are executed, in which case it'll conclude that this app might have a source sync flow. So the string latitude is tainted by location data, and then the first runnable, run malice, is going to send the location data to the internet if it's executed. So in order to find the source sync flow, our analysis encodes the semantics of the program in a labeled graph. So the vertices in this graph are the sources and sinks, and as well as the program variables. And the edges encode the relations between these vertices. So for example, here's the location source, and get latitude. The return value of get latitude is tainted by the location source. Here's the argument of send HTTP, and that flows to the internet. The first line of the program, there's an assignment from the return value of get latitude to the lat variable in the program. And on the fourth line of the program, there's an assignment of the lat variable to the argument of send HTTP. So at this point, our analysis can already find the source sync flow. And to do so, we actually run a context-free reachability problem. But for the purposes of this talk, I'm just going to think about it as a regular graph reachability problem. And the details of how to generalize everything we do are in the paper. So here, there's a path from location to internet, so our information flow analysis will find a source sync flow. And then the rest of the code isn't really relevant to the information flow, so I'm not going to, so I omit it from the graph. So to begin with, we're going to assume that all of the code is potentially dead. And then, as I said earlier, we want to try to find a subset of edges that we can remove from the program in order to produce a valid program that doesn't have any information flows. So what we're going to do is we're just going to add some weights to the edges. So edges that we can't remove are going to be given weight infinity, and then any edges that correspond to statements in the program that might be dead are going to be given weight 1. So these are the edges that we're willing to remove from the program. And we're just going to run a min-cut algorithm over this graph. Let's say the min-cut algorithm returns this first assignment edge. So that corresponds to the first program statement over here. So we're going to propose this statement to the auditor, to the developer, and then the developer can respond with a test case that basically just executes these lines of code, these 10 lines of code. And then we can take that test case, check that, okay, everything is reachable except line 4, except possibly line 4. And then we'll update the weights in our graph. So now the first assignment edge, we update the weight to infinity because it can't be cut anymore. And then we'll just run a min cut again. If the developer says that this new cut is valid, then we'll just insert some instrumentation that throws an error just before this statement is executed. And then this app is safe, so we can publish it on the App Store. So one shortcoming of our process is that if a developer mistakenly answers yes, so then we might delete some important code from the application. And while we can't solve this problem, we can try to mitigate it, and we'll do so by computing multiple independent cuts. So the developer only needs to be right once in order for the program to be valid. And how we're going to do this, well, we're going to proceed as initially as before. So we compute our first cut, which is the assign statement. And we're going to immediately say, OK, let's suppose that this statement is reachable. So we're going to add it to our reachable set. And then we're going to compute another cut right away before querying the developer. So we'll find the second assignment edge in this case. And now we'll just propose both cuts to the developer. And even if the developer makes a mistake and says that both cuts are reachable, we're going to, because the second cut is valid, the second cut is dead code, so we know that the flow is a false positive. So if the developer responds valid, then we can instrument the app to terminate only if every cut is reached. So because the program is correct as long as any cut is valid, this instrumented app is still going to be safe. It's not going to exhibit any information flows. So we implemented this interactive verification process on a we implemented this interactive verification process and ran the tool on a corpus of 78 Android apps. So in the first experiment, we just recorded the cut sizes to make sure that the cuts were small enough that a developer could reasonably verify them. And in the second experiment, we actually performed the role of the developer, took some of the cuts and interactively verified them, the apps. So in the first experiment, we just looked at some cut sizes. So here I've binned the apps into 3 bins, small, medium, and large, and all apps on the far right. And we computed 2 cuts. So the average size of the first cut is shown in red, and the average size of the second cut is shown in black. So as you can see, on average, all of the cuts are quite small. Even for large apps, they're only about 13 statements. And we believe that this is quite reasonable. So the developer just has to check these 13 statements and determine if they're reachable. And in the second experiment, we actually played the role of the developer to see kind of how many interactions we would need to do before we find a valid cut. So we focused on the 12 false positive information flows. So we started with 78 apps. For 66 of these apps, our tool actually didn't find any false positives. All the flows we found were true positives. And for the remaining 12 apps, there was a false positive information flow. So if it's a true positive, obviously there isn't a valid cut, which is why we focused on these 12 apps. So we just generated some cuts. As with the last experiment, we generated 2 cuts. And in black, I'm showing the cumulative number of apps remaining in the process. So the interactive verification process is going from left to right. After generating the first 2 cuts, for 7 out of the 12 apps, one of these 2 cuts was valid, so we could just remove that cut from the program and get a correct program that we could put on the App Store. And then for the remaining 5 apps, we repeated this process, generated some new cuts, and we verified 4 out of the 5 remaining apps. And that just leaves 1 app that we had to actually give to the auditor. And for this app, the false positive wasn't due to dead code, so there was no valid cut to be found. So just to summarize, our interactive verification process helps us remove dead code from the app with the input of a possibly adversarial developer. And in our experiments, we showed that we discharged 11 out of the 12 false positives using just 2 interactions with the developer. And what we've shown really is that just adding a little bit of interaction can really go a long way to helping remove some of the manual labor that's present in so-called automatic static analyses. And in this project, we focused on filtering out false positives due to dead code. And we showed that this is really an effective strategy. But that by interacting with, in this case, the developer, we can really effectively reduce the workload needed to filter out these kinds of false positives. So just some future work, we want to consider other sources of false positives beyond dead code, for example, reflective method calls, implicit flows, and so forth, and also think about more complex security policies beyond those captured by information flows. So thanks for listening, and I'll be happy to answer any questions. Okay. Hi.